Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to just imagine something for a second. You are standing outside on a perfectly clear, crisp night. You're far away from the city lights, maybe out in the high desert of Chile or up in the Rocky Mountains.
The best spots, really.
Yeah, exactly. So you let your eyes adjust to the dark, you tilt your head back, and you just look up at the night sky.
Oh, well.
And it is completely overflowing with stars.
It's a staggering view.
It really is.
Yeah.
You see the constellations you recognize, and cutting right across the center of your view is that glowing, hazy, complicated structure of the Milky Way.
Right.
When you stand there taking it all in, it's totally instinctual to think that you are looking at the universe. You feel like you're seeing the true census of our galaxy,
Oh, absolutely. We all do that.
But what if I told you that the most massive, the most dense, and the most gravitationally powerful inhabitants of that galaxy are entirely invisible to you?
Yeah, hiding in plain sight.
Right. What if they are wandering silently in the dark, just weaving through those star fields completely undetected?
It really forces a total reevaluation of what we consider, the galaxy to actually be.
Totally.
Because we are incredibly biased by our own biology. Our eyes evolved to detect the electromagnetic radiation emitted by our sun, so we naturally equate the presence of matter with the presence of light.
If something is there, it shines.
Right. We assume it shines, reflects, or glows. But the reality of the Milky Way's mass distribution is, it's much stranger than that.
How so?
Well, the most significant stellar remnants, specifically stellar mass black holes, they are not the ones emitting blinding radiation.
Right. Which is wild to think about.
It is. For over half a century, the entire field of high-energy astrophysics has built its models of black hole demographics on this highly visible, incredibly loud minority.
Like the ones making all the noise.
Exactly. We've extrapolated our theories from the black holes that are locked in tight binary systems, the ones interacting violently with a companion star.
But there's a catch, right?
Yeah, there has always been this underlying mathematical suspicion that these glowing X-ray emitting black holes were the bizarre outliers, not the standard.
Okay, let's unpack this, because this is a fundamental shift in how we understand the population dynamics of the Milky Way.
A massive shift.
Today, we are going to explore this groundbreaking realization about our hidden galactic underworld.
I love that term, galactic underworld.
It fits so well. We're going to look at how new models, specifically some incredibly detailed computational work coming out of the Flatiron Institute, are entirely rewriting the biography of stellar mass black holes.
Right, down to the very foundations.
We need to look at how they form, how they survive the violence of their own birth, and how they quietly traverse the galaxy without us ever knowing they were there.
To even begin grasping the scale of this hidden population, we have to completely dismantle our observational biases.
Which is hard to do.
It is very hard. The reason we are suddenly on the hunt for isolated black holes requires us to look at the historical limitations of how we, as observers, bound to a rocky planet, have been forced to study them.
Right.
It all comes down to the fundamental physics of the event horizon and the mechanics of accretion.
Right, because by definition, an isolated stellar mass black hole is the ultimate cosmic camouflage.
It really is.
We are talking about the collapsed core of a massive star, packing anywhere from, 5 to maybe 50 solar masses into a sphere with a radius of a few dozen kilometers.
Yeah, incredibly dense.
And the escape velocity at the event horizon exceeds the speed of light. So they cannot emit light at any wavelength.
None at all.
Not optical, not infrared, not ultraviolet.
And this is exactly where the history of astronomy painted us into a corner. Before the dawn of space-based X-ray telescopes in the 1960s and 70s, black holes were largely a mathematical curiosity.
Just equations on a chalkboard.
Exactly. They were a solution to Einstein's field equations of general relativity that many physicists, including Einstein himself at times, honestly thought nature would somehow find a way to prevent from actually forming.
They thought it was too weird to be real.
Right. It wasn't until instruments like the Uhuru satellite launched that we started detecting these blazing points of X-ray emission in the sky, like Cygnus X1.
And Cygnus X1 wasn't just glowing, right? It was flickering on these millisecond timescales.
Yes, which is the crucial detail.
Because if it flickers in 1,000th of a second, the object itself can't be much larger than the distance light travels in 1,000th of a second.
That is the exact logical deduction that proved they existed in reality.
It's so brilliant.
It really is elegant physics. But notice what we were detecting there. We weren't detecting the black hole itself.
We were detecting the plasma.
Exactly. Almost all the stellar mass black holes we have definitively characterized have been found in X-ray binary systems.
So you have a compact object locked in a tight gravitational dance with a massive main sequence companion star, like a blue supergiant.
And that gravitational dance is anything but peaceful.
Oh, I imagine it's incredibly violent.
It is. If that companion star expands as it ages, or if the orbit is just tight enough, the black hole's gravity begins to literally strip the outer layers of hydrogen and helium right off the star.
It's literally tearing its neighbor apart.
Yeah, it's a process called Roche-Lobe overflow.
Roche-Lobe overflow.
Right. The companion star swells beyond its gravitational boundary, and the stellar material gets funneled toward the black hole. But it doesn't fall straight in.
Because everything in space is spinning.
Exactly. Because the system is rotating, the infalling gas has angular momentum. It spirals inward, forming this flattened accretion disk around the equator of the black hole.
I want to spend a second on the physics of that disk because it's literally the only reason we've been able to study black holes at all up to this point.
It is the only signal we get.
And it's not just gas swirling down a drain, right? It's plasma behaving under extreme magnetohydrodynamic forces.
The conditions inside that disk are hellish. I mean, truly hellish.
How hot are we talking?
Millions of degrees. As the gas spirals closer to the event horizon, the orbital velocities approach a significant fraction of the speed of light.
Wow.
But the inner layers of the disk are orbiting much faster than the outer layers, which creates immense shear.
So they're grinding against each other.
Exactly. You have adjacent layers of plasma rubbing against each other at near light speed. This viscous friction, which we now understand is heavily driven by magnetic turbulence, specifically something called the magnetorotational instability, heats the gas to millions of degrees Kelvin.
So it gets so hot that the thermal radiation peaks in the X-ray part of the electromagnetic spectrum.
Right. It blasts out high-energy photons, and in many cases, you get these powerful relativistic jets shooting out from the magnetic poles.
And those X-rays are what hit the detectors on our satellites.
Yep. Or, conversely, we look at the companion star, and we observe its radial velocity.
So we see it wobbling.
Exactly. We see the spectral lines of the star blue shifting and red shifting as it is whipped around this invisible center of mass. We calculate the mass of the unseen partner using Kepler's laws.
The old school orbital math.
Right, hundreds of years old. And if the mass is above the Tolman-Oppenheimer-Volkoff limit, which is the theoretical maximum mass for a neutron star, around 2 to 3 solar masses, we deduce that the invisible partner just has to be a black hole.
So basically, every piece of empirical data we have, the mass distributions, the spin parameters, the orbital periods, it's all derived entirely from systems where a black hole is actively cannibalizing a neighbor.
100%.
We see the destruction it causes, and we build our models of galactic astrophysics based solely on the perpetrators of that destruction.
Which brings us to the core problem of observational bias.
Right.
What happens if a black hole does not have a companion star? What if it is just wandering through the interstellar medium entirely alone?
Well, the space between the stars is incredibly sparse.
Right? It is. We call it a vacuum, but it's not totally empty. It's filled with tenuous clouds of neutral hydrogen and ionized gas.
But the density of that interstellar medium is what, maybe 1 atom per cubic centimeter on average?
Yeah, in the cold neutral medium, maybe tens of atoms per cubic centimeter, but still functionally a vacuum compared to anything on Earth.
Right.
If an isolated black hole, say 10 times the mass of our sun, moves through that medium, it does exert a gravitational pull on that sparse gas.
It has gravity.
Right. It goes through a process called Bondy-Hoyle-Littleton accretion. It sweeps up a tiny, tiny fraction of that gas as it travels.
But compared to ripping entire layers off a supergiant star, sweeping up a few stray hydrogen atoms isn't going to generate the kind of friction needed to produce X-rays.
Not even close. The accretion rate is so infinitesimally low that the gas barely heats up at all.
It's basically starving.
Yes. It certainly doesn't form a blazing, optically thick, geometrically thin accretion disk. The radiation emitted by a solitary black hole accreting from the interstellar medium is so faint that it is utterly undetectable by our current X-ray or radio observatories.
So they produce no glowing debris.
None. They leave no wake that we can see.
Wow. It's such a profound realization when you think about the history of science.
It really makes you second-guess everything.
Right, because our entire foundational knowledge of these cosmic objects, the formation models we teach in universities, the evolutionary tracks we assume they follow, is based purely on the messy eaters.
Exactly. We've been studying the anomalies.
Yeah, the extreme edge cases of stellar remnants, and just assuming they represented the standard galactic population.
It's a classic selection effect.
Give me an analogy here because it's so wild to think about.
Okay. It's akin to trying to understand the demographics, behavior, and daily habits of all marine life. But your only method of observation is studying the fish that happen to jump out of the water and land on the deck of your boat.
That's hilarious and terrifying for science.
Right. You are going to come away with a highly skewed data set. You'll think the ocean is entirely populated by flying fish.
You'd have no idea sharks or whales even existed.
Exactly. Every time astronomy realizes that its view is limited by its observational tools, the universe suddenly gets much larger and much more complex. Acknowledging that we have been blinded by the blazing light of X-ray binaries is one of those monumental paradigm shifts.
So, if we accept this premise that there are invisible, gravitationally immense objects wandering the galaxy completely silently, how do we study them?
That is the million-dollar question.
Right, because if they don't emit X-rays, if they don't have a companion star to wobble around, we can't point a telescope at them. We can't take a picture. We can't use spectroscopy.
Nope, nothing traditional works.
So how do we even begin to figure out how many of them there are or where they might be hiding?
Well, if you can't observe the current state of the galaxy directly, you have to build your own galaxy from scratch.
Right, really?
Yeah, you have to rewind the clock to the formation of the Milky Way and let the physics play out in a controlled environment.
You simulate the universe.
Exactly. Until our observational techniques catch up to our theoretical physics, population synthesis simulations are the absolute most powerful tool we have to uncover this hidden population.
And this is where the new research comes in.
Yes. This is where the work led by Tom Wag and the team at the Flatiron Institute becomes so critical.
Right.
They recognized this massive blind spot in the empirical data, the fact that X-ray binaries were skewing our understanding of stellar death. So they decided to tackle the problem computationally.
Okay.
They developed an incredibly detailed, massive-scale simulation of the Milky Way's entire evolutionary history.
Let's define what we mean by history here, because we aren't talking about human timescales or even the lifespan of the Earth, right? We're talking about deep cosmological time.
We're talking about roughly 13 billion years of galactic evolution.
13 billion years.
Yeah. And to do this, they couldn't just model a few stars. They had to model the entire life cycle of a representative galactic population.
From start to finish.
Yes. They tracked how stars coalesce from giant molecular clouds of gas and dust. They modeled how those stars evolve over millions or billions of years depending on their initial mass. And crucially, they modeled the exact mechanisms of how those stars eventually die.
I have to pause and push back on the methodology here.
Go for it.
Because the immediate skeptical response, I think, for a lot of people is, if a simulation is, at its core, just a really complex computer program, how can we trust it to tell us about a population of black holes we've literally never seen?
It's a fair question.
Aren't we in danger of circular reasoning? Like we program our own assumptions into the code, and the computer just spits our assumptions back out at us.
Right, the garbage in, garbage out problem.
Exactly. If we don't know the exact star formation rate from 10 billion years ago, how can we trust the output of the simulation today?
That is the necessary skepticism that computational astrophysicists live with every single day. The validation of these models is the hardest part of the job.
So how do they justify it?
Here's why this isn't just an exercise in circular logic. We aren't making up the rules of stellar evolution. We are relying on the hard, empirically proven laws of thermodynamics, quantum mechanics, and general relativity.
So you're saying the underlying physics engine of the simulation is locked in by what we can prove in a lab or observe in the nearby universe right now.
Precisely. We know the nuclear physics of how hydrogen fuses into helium. We have excellent, rigorously tested models of stellar structure.
Stuff we've known for decades.
Yeah. We know that a star of a certain mass with a certain metallicity, meaning the amount of elements heavier than helium it contains, will burn its fuel at a specific rate, swell into a red giant or a Wolf-Rayet star, and eventually undergo core collapse.
But what about the initial conditions? How do you know what to feed into the simulation at the very beginning, 13 billion years ago?
That is where things get complex and where we have to use something called the initial mass function, or IMF.
The IMF, okay, what is that?
The IMF is an empirical rule that describes the distribution of masses for a newly formed population of stars.
Oh, like a statistical bell curve.
Sort of, yeah. Decades of observing stellar nurseries like the Orion Nebula have shown us that for every massive O-type star born, nature produces hundreds of tiny, low-mass M-type red dwarfs.
Okay, so a lot of small stars for every big one.
Right. We apply that statistical distribution to our virtual galaxy. We also input the star formation history, how the rate of star birth peaked around what we call cosmic noon about 10 billion years ago, and has slowly tapered off since then.
So you take the IMF, the star formation history, the metallicity gradients across the galactic disk, and those ironclad rules of stellar evolution, and you just let the code run forward.
Yes, and we include one more critical variable, the binary fraction. We know from observing massive stars today that the vast majority of them, the O and B type stars that eventually become black holes, are not born alone. They are born in binary or even triple systems.
Which is so different from our sun.
Very different. So the simulation has to track the gravitational interactions, the mass transfer, and the tidal forces between these virtual stars over millions of years. When you let all those physical equations interact over cosmic timescales, the simulation isn't guessing. It is calculating the inevitable mathematical reality of what must be out there today.
It's essentially incredibly complex forensic accounting, but instead of tracking money, you are tracking mass and momentum across billions of years.
I love that analogy. And we know the simulation is largely accurate because we can check its present-day output against the things we can see.
Ooh, clever.
Right. If the simulation finishes its 13 billion year run and produces a population of visible stars, white dwarfs, and X-ray binaries that actually matches the observed Milky Way,
then you know the math works.
Exactly. Then we can be highly confident that the invisible population it produced alongside them is also accurate. The visible universe acts as a calibration tool for the invisible universe.
The computational scale of what you were describing is just staggering.
It is massive.
You are tracking the births, the chaotic mass transfer phases, and the spectacular deaths of millions of representative stellar populations. You are calculating the gravitational dynamics. You are factoring in the mass they lose through intense stellar winds.
Which is a huge factor.
Because massive stars can blow away huge fractions of their own mass before they even die. Right.
Oh, yeah. They shed mass constantly.
And you are doing all of this across a simulated canvas representing the 100,000 light-year disk of the Milky Way.
It requires immense computing power, often utilizing Monte Carlo methods to handle the probabilistic nature of stellar evolution.
Rolling virtual dice based on physics.
Yes. And the reason you need that level of granular step-by-step detail is because the birth of a black hole is not a clean, simple mathematical transition.
It's not a gentle fade to black.
No. It is one of the most violent, chaotic, and messy processes in the universe. The simulation has to model the exact physical mechanics of stellar death, because the manner of death dictates the entire future trajectory of the resulting black hole.
Which brings us to the core collapse.
The big moment.
Right. This is where the simulation reveals why so many of these black holes end up completely alone. Stellar mass black holes are forged in the fires of core collapse supernovae.
Let's break down what actually happens inside the star, because the physics of the explosion are what drive the kinetics of the black hole.
Okay, walk me through it.
Imagine a star 20 or 30 times the mass of our sun. For millions of years, it has maintained hydrostatic equilibrium.
Which means it's balanced, right?
Exactly. The outward pressure of nuclear fusion in the core perfectly balances the inward crush of its own immense gravity. It fuses hydrogen to helium, helium to carbon, carbon to oxygen, all the way down the periodic table until it builds up a core of solid iron.
And iron is the ultimate cosmic dead end.
Iron is the ash of the stellar engine. You cannot extract energy by fusing iron. It actually requires more energy to fuse iron than the reaction releases.
There's an energy deficit.
Right. So suddenly, the outward radiation pressure ceases. The core, which is roughly the size of the Earth but contains more mass than our sun, is left entirely at the mercy of gravity.
That is terrifying depiction.
It is. It is supported only by electron degeneracy pressure.
Which is what?
It's a quantum mechanical rule that says electrons resist being squeezed into the exact same quantum state.
But if the iron core exceeds the Chandrasekhar limit, which is about 1.4 solar masses, right?
Yeah, 1.4.
Then even quantum mechanics can't hold up the weight of the star.
Gravity always wins. In a fraction of a second, the core collapses inward at a significant fraction of the speed of light.
A fraction of a second.
Literally milliseconds. The density becomes so extreme that electrons and protons are crushed together to form neutrons, releasing a massive burst of neutrinos. If the progenitor star is massive enough, the collapse doesn't stop at the neutron star phase.
It just keeps going.
It continues collapsing entirely past its own event horizon, forming a singularity. The black hole is born.
Meanwhile, the rest of the star, all those outer layers of hydrogen, helium, and carbon, are suddenly left with no core supporting them.
Right, the floor falls out.
So they come crashing down in free fall. They hit the unbelievably dense, newly formed compact object at the center, and they bounce.
The physics of that bounce are incredibly complex. The infalling material hits a rigid wall of nuclear density. A shockwave forms and begins propagating outward.
Blasting the star apart.
Well, eventually. But the shockwave actually stalls at first. It loses energy as it tries to push through the immense weight of the infalling star, and energy is lost through the photodisintegration of iron nuclei.
So what pushes it over the edge?
What revives the shockwave, what actually powers the supernova explosion, is that initial burst of neutrinos from the core.
Oh, wow. The neutrinos get trapped in the extremely dense matter behind the shock front. They deposit their kinetic energy, and they literally blow the outer layers of the star into space.
Exactly. The light from that explosion can briefly outshine the entire host galaxy.
Now, in an idealized, simplified physics textbook, you might picture that explosion expanding outward perfectly symmetrically, right? Like a perfect expanding sphere of glowing plasma.
But nature abhors a perfect sphere.
Especially in a collapsing star.
Right. Real stars are rotating. They have intense, twisted magnetic fields. And crucially, the region behind the stalled shockwave is boiling with intense convective currents. The neutrino heating is not uniform.
So it's turbulent.
Highly turbulent. Astrophysicists model this using something called the standing accretion shock instability, or SAS-I.
Okay, SAS-I.
Basically, the shock front actually sloshes back and forth inside the collapsing star.
Like water in a bathtub.
Yeah, exactly. This means that when the explosion finally breaks out, it is almost always asymmetrical. The shockwave blasts out significantly stronger in one direction than another, plumes of high-velocity ejecta shoot out asymmetrically, and the neutrino emissions themselves might be lopsided.
And here is where we get to the kinematics that change everything. Because of the conservation of momentum, Isaac Newton's third law of motion, that asymmetry has a massive physical consequence for the newly formed black hole sitting at the center of the blast.
For every action, there is an equal and opposite reaction. Because the supernova blasts more mass and kinetic energy in one direction, the incredibly dense black hole left behind is catapulted in the exact opposite direction.
It gets launched.
Yes. We call it a natal kick, or a supernova recoil kick.
I always try to visualize this with the classic physics analogy of firing a massive cannon while standing on a completely frictionless sheet of ice.
It's a great visual.
Right. When the gunpowder detonates, the cannonball blasts forward, but the heavy iron cannon itself recoils violently backwards, sliding across the ice. In this scenario, the star's outer layers are the cannonball blasting out into the interstellar medium, and the brand new black hole is the heavy cannon recoiling in the opposite direction.
It's a highly effective analogy, but we have to scale up the energy by orders of magnitude that are just hard for the human brain to process.
Fair enough.
The Flatiron simulation modeled the forces of these asymmetric supernovae based on observational data from pulsar velocities, and the resulting natal kicks are breathtaking.
How fast are we talking?
We are talking about black holes objects with the mass of 10 or 20 suns being instantly accelerated to velocities of tens and sometimes hundreds of kilometers per second relative to their original orbit in the galactic disk.
100 kilometers per second. That's roughly 220,000 miles per hour.
Right.
And it's a mass of 10 suns moving that fast. But the simulation revealed that the high-end tail of that velocity distribution is even more extreme.
This is where it gets crazy.
Yeah, this brings us to the most mind-bending statistic from the entire study. Roughly 3% of all stellar mass black holes ever formed in the Milky Way pick up so much speed from their natal kicks that they achieve escape velocity.
Yes.
They are kicked so hard they literally break the gravitational bonds of the galaxy and leave completely.
The physics required to achieve galactic escape velocity are staggering. Think about the gravitational potential well of the Milky Way.
It's huge.
You aren't just escaping the pull of the local star cluster. You are fighting the combined gravitational mass of hundreds of billions of stars, the supermassive black hole at the galactic center, and, most importantly, the massive invisible halo of dark matter that envelops the entire galaxy.
Depending on where the star is located in the galactic disk, what kind of speed do you need to actually achieve escape velocity?
In the solar neighborhood where we are, you need to be moving at roughly 550 kilometers per second relative to the galactic center to escape the Milky Way entirely.
550 kilometers per second.
That is over 1.2 million miles an hour.
Imagine the sheer, localized cosmic violence required to generate a recoil kick that accelerates a 10 solar mass black hole to over 1 million miles an hour. The energy scales are terrifying.
It is one of the most energetic kinematic events in the universe, short of a supermassive black hole merger. And the cosmological implications of that 3% figure are just profound.
Because it means they are out there.
Exactly. We tend to think of the intergalactic void, the space between galaxies, as entirely empty, just a freezing, radiation-filled vacuum. But if 3% of all stellar mass black holes ever created in the history of our galaxy have been ejected, that means the intergalactic medium is not empty at all.
It is populated by millions of these ejected, ultra-fast, completely silent wanderers.
Millions of them.
There are rogue black holes shooting through the nothingness between the Milky Way and the Andromeda Galaxy right now.
They are essentially ballistic gravitational warheads cruising through the dark, completely disconnected from any galactic structure. They will never interact with another star. They will never accrete gas. They will simply travel through the expanding void of the universe until they evaporate via Hawking radiation trillions of years from now.
It sounds like the premise of a sci-fi horror novel, but it is just the inevitable mathematical result of momentum conservation.
Math is scary sometimes.
It really is. Okay, but let's reel it back in from intergalactic space. 3% are kicked so hard they leave the galaxy entirely. What happens to the other 97%? The ones that get a violent natal kick, but not quite hard enough to climb out of the dark matter halo? What happens to them inside the Milky Way?
This is where we return to the binary problem. As we discussed earlier, the vast majority of the massive ONB-type stars that produce black holes are born in binary pairs.
Right.
So imagine two massive stars orbiting each other. The primary star, the more massive one, ages faster. It goes supernova. Two things happen simultaneously that spell the end for that binary relationship.
First, there is the mass loss.
Right. It's called the Blau kick. When the star explodes, it ejects a huge portion of its mass into space at a significant fraction of the speed of light. Because gravity is dependent on mass, the gravitational tether holding the two stars together suddenly drops.
Because the mass is just gone.
Exactly. If the exploding star loses more than half of the total mass of the binary system, the system becomes gravitationally unbound immediately. The companion star just flies off in a straight line, completely untethered.
That explains the runaway stars we sometimes see streaking across the galaxy, producing massive bow shocks in the interstellar medium. They are the surviving companions of a broken binary.
Exactly. So you have the mass loss unbinding the system, but then you add the asymmetric natal kick we just talked about.
The million-mile-an-hour cannonball.
Right. The newly born black hole is suddenly rocketing off at 100 kilometers per second in a random direction. Between the sudden loss of mass and the violent kinetic kick, the overwhelming majority of binary systems do not survive the supernova of the primary star. The gravitational bond just snaps.
And this is where the Flatiron simulation delivers its critical demographic census.
The big reveal.
Yeah. By tracking millions of simulated stellar binaries, calculating the mass loss during the supernova, and computing the exact trajectories of the natal kicks, the model reveals that around 91% of the Milky Way's stellar mass black holes are currently isolated.
91%.
Over 9 out of 10 stellar mass black holes in our galaxy are wandering completely alone.
Yes.
They are not in binaries. They are not accreting gas from a companion. They are not emitting X-rays.
They are kinematically decoupled from their birth clusters, drifting silently through the galactic disk and the galactic halo. There is no glowing accretion disk to give them away. They are functionally invisible.
This requires a massive cognitive restructuring of how we view high-energy astrophysics.
It does.
Let's trace the logic of what this means for the field. If 91% of the population is completely isolated and invisible, then our entire textbook picture of a black hole, the swirling, blazing disks of superheated plasma, the relativistic jets, the violent consumption of a neighbor star is actually a bizarre, rare exception.
Very.
We have been looking at the surviving 9%, the ones that somehow managed to stay gravitationally bound after the supernova, and assuming they represented the normal state of affairs.
The simulation forces us to confront the fact that a normal stellar mass black hole is not a glowing engine of cosmic destruction.
Far from it.
Right. The normal baseline state of a stellar remnant is a cold, silent, solitary nomad. It highlights a massive selection bias that has permeated astronomy for decades.
It's like trying to formulate a comprehensive theory of human sociology. But your methodology dictates that you are only allowed to study people who are currently playing the drums in a heavy metal band on a brightly lit stage.
That is exactly what it's like.
You are going to come away with a very skewed, highly energetic idea of what the average human being does on a Tuesday afternoon.
If you only study the heavy metal drummers, you assume the entire population is loud, energetic, and constantly interacting with an audience. You completely miss the vast majority of introverts reading quietly in the library.
The silent majority.
Exactly. In the galactic context, 91% of the black hole population are extreme introverts.
And this isn't just a trivial demographic correction. This hidden population fundamentally changes how we understand the mass distribution of the Milky Way.
It changes everything.
It forces us to rewrite the models of galactic chemical enrichment, because the supernovae that form these black holes distribute heavy elements differently depending on their kinetic environment.
Right. The metals get spread differently.
It even impacts the cutting-edge field of gravitational wave astronomy.
That is a crucial point, actually. Instruments like LIGO and Virgo detect the ripples in space-time caused by two black holes merging.
The chirp.
Right, the chirp. But if 91% of black holes are born single or become single immediately after birth, how are we detecting so many mergers?
It's a paradox.
It forces theorists to heavily investigate dynamical assembly models, the idea that these single black holes migrate into dense environments like globular clusters, where they gravitationally capture each other in close encounters, rather than evolving from isolated binary stars. You cannot accurately calculate merger rates without knowing the true isolated binary fraction. We have to account for the silent majority to make the math work.
Okay, so this brings us to the ultimate observational challenge. Thanks to the computational power of the Flatiron models, we now have this incredibly detailed simulated map of the galaxy.
We have the blueprint.
Right. We know it should be absolutely teeming with invisible solitary black holes. We know roughly how many there are in the tens of millions to 100 million. We know where they should be clustered based on historical star formation rates. And we know the velocity distribution of those natal kicks. We possess the theoretical map. But how do we actually transition from theoretical simulation to empirical discovery?
You have to get creative.
How do you hunt an invisible nomad?
You have to fundamentally change your observational paradigm. You have to stop looking for the black hole itself.
If you can't see it.
Exactly. You have to stop looking for X-rays or accretion disks. Instead, you have to look for the one physical property a black hole cannot hide, no matter how isolated it is. It's gravity. You have to look for the distortion of space-time itself.
We are diving into the realm of general relativity. We're talking about gravitational lensing.
Exactly. Albert Einstein's field equations demonstrated that mass dictates the curvature of space-time. Massive objects warp the fabric of the universe around them.
Like a bowling ball and a trampoline.
The classic example. Now, light naturally wants to travel in a straight line along geodesics. But if that light passes near a massive, dense object like a black hole, the curved geometry of space-time forces the light path to bend.
So the black hole acts as a literal lens.
It operates on the exact same optical principles as a glass lens, just driven by gravity instead of electromagnetism. Specifically, astronomers were looking for a phenomenon called gravitational microlensing.
Let's break down the mechanics of microlensing, because the precision required to detect this is just mind-boggling.
It really is.
Imagine you were trying to spot a perfectly clear, solid glass sphere rolling across a forest floor that is covered in brightly colored autumn leaves.
Okay, great visual.
You cannot see the sphere itself. It is completely transparent, doesn't emit any light of its own, and it blends in perfectly with the shadows. But as it rolls directly in front of a brightly colored red leaf, the curvature of the glass gathers the light from that leaf and focuses it. For a brief second, you see the leaf behind the sphere suddenly look magnified and much brighter. And then as the sphere continues rolling, the leaf fades back to its normal appearance. You spot the invisible sphere entirely by watching how the background environment briefly distorts and magnifies as the object passes by.
That is a perfect macroscopic visualization of microlensing. In the galactic context, we aim our telescopes at a dense field of distant background stars, usually looking toward the galactic bulge where the star density is highest.
Because you want maximum leaves on the floor.
Exactly, you want a busy background. If one of these solitary, invisible black holes happens to drift directly between our telescope and one of those distant background stars, the black hole's intense gravity acts like that rolling glass sphere. It bends and focuses the starlight toward Earth.
And what does that look like through a telescope?
Well, for a period of a few weeks or months, depending on the relative velocity of the black hole, that distant background star will appear to slowly brighten. It forms a very specific symmetrical light curve called a Paczynski curve, and then it will gradually fade back to its normal baseline brightness as the black hole continues on its trajectory.
But here is the major observational hurdle, right?
Oh, yeah.
Normal, dim stars also have mass. If a faint red dwarf or a brown dwarf passes in front of a background star, it will also act as a gravitational lens. It will also cause the background star to temporarily brighten. So how do we differentiate between a microlensing event caused by a boring low-mass red dwarf and a microlensing event caused by a 10 solar mass isolated black hole?
That is the degeneracy problem in photometric microlensing.
The degeneracy problem.
Right. If you only measure the change in brightness, you cannot definitively prove the mass of the lensing object. The timescale of the brightening event is a combination of the object's mass, its velocity, and its distance from Earth.
So a slow, small thing looks like a fast, big thing.
Exactly. A slow-moving, low-mass star could produce the exact same brightening curve as a fast-moving, high-mass black hole. To break that degeneracy, you need a tremendous leap in observational technology. You need to move beyond photometric microlensing and achieve astrometric microlensing.
Astrometric microlensing. Astrometry is the precise measurement of a star's position in the sky.
Right. When a massive black hole passes in front of a star, it doesn't just magnify the light. The asymmetrical bending of the light rays actually causes the apparent position of the background star to shift on the sky.
It moves.
The centroid of the light literally moves. It looks like the background star has been physically dragged a microscopic distance from its true location, tracing out a tiny ellipse before returning to its original position.
So the background star gets brighter, and it looks like it physically wobbled its position in the sky.
Exactly. And the size of that astrometric shift is directly proportional to the mass of the lensing object. A low-mass red dwarf will cause a minuscule positional shift. A 10 solar mass black hole will cause a significantly larger astrometric shift.
That's the smoking gun.
It is. If we detect that massive gravitational signature, the long-duration brightening combined with a large astrometric wobble, but we detect absolutely zero light coming from the lensing object itself, we know we have caught a ghost. We know we have definitively found an isolated stellar mass black hole.
But we have to clarify the scale of the wobble we are talking about here.
Oh, it's incredibly small.
Right. The distances involved are astronomical. We are measuring the positional shift of a star tens of thousands of light years away, caused by an invisible object that is also thousands of light years away.
The required precision is almost unfathomable. We are talking about measuring an astrometric shift of a few milliarc seconds, or even microarc seconds.
A microarc second.
Yeah. To put that angular resolution in perspective, a microarc second is roughly equivalent to measuring the diameter of a human hair located in Paris from a telescope sitting in New York City.
That is just, that's absurd.
It's an observational feat that was considered practically impossible until the last few years. But this is exactly where the future of astronomy is pivoting. We are currently building and deploying the exact tools needed to execute this cosmic treasure hunt.
Let's talk about the hardware, starting with the Nancy Grace Roman Space Telescope.
The Roman Space Telescope is going to revolutionize this specific field of study. It is an infrared observatory designed with a massive field of view, roughly 100 times the field of view of the Hubble Space Telescope, but with the same deep resolution.
Wow.
And because it operates in the infrared, it can peer straight through the thick clouds of interstellar dust that block optical light.
Which is critical, because you want to point the telescope directly at the galactic center, where the background stars are most densely packed, to maximize your chances of seeing an alignment.
Precisely. Roman is going to stare at hundreds of millions of stars simultaneously in the galactic bulge, running a dedicated microlensing survey. It will continuously monitor their brightness, watching and waiting for those specific symmetrical brightening events that indicate a massive object is passing through the line of sight.
So it's basically a nest.
Yes, it is a statistical dragnet designed to catch these events in bulk.
But Roman primarily handles the photometric side, the brightening, to get that critical positional shift. To measure the micro-arc-second wobble that proves the mass of the black hole, we have to look to Europe. We have to talk about the Gaia mission.
Oh, Gaia. The European Space Agency's Gaia Observatory might be the most quietly revolutionary mission in the history of astronomy.
It doesn't get a lot of press.
It doesn't, because it doesn't produce the spectacular, colorful nebula photos that the James Webb Space Telescope does, so it doesn't get as much public attention. But its scientific output is foundational. Gaia's singular purpose is astrometry.
It is essentially creating a three-dimensional, dynamically moving map of the Milky Way.
Gaia is positioned out at Lagrange point 2, slowly spinning, using two telescopes with a fixed angle between them to continuously scan the entire sky. It measures the exact positions, distances, and proper motions of over 1 billion individual stars with unprecedented micro-arc-second precision.
And it does this over and over again, right?
Exactly. As it scans the sky repeatedly over its mission lifetime, it is perfectly positioned to detect the minute astrometric shifts caused by invisible black holes acting as gravitational lenses.
So you combine the deep, wide-field infrared photometric data from the Roman Space Telescope with the ultra-precise all-sky astrometric data from Gaia.
You merge them.
You cross-reference the brightening events from Roman with the positional wobbles from Gaia.
And you combine that with large-scale spectroscopic surveys from ground-based telescopes, which measure the radial velocities and chemical makeup of the background stars to ensure we understand the baseline properties of the objects being lensed.
It's a team effort.
It really is. We are building a multi-layered, multi-wavelength observational net specifically designed to catch these isolated nomads.
Which brings us completely full circle back to the Flatiron Institute's models. Tom Wagg's simulations aren't just an interesting theoretical exercise in computational astrophysics. They are a literal treasure map.
That is exactly how the observational teams view it. The simulation tells the Roman and Gaia scientists what the expected yield should be. It predicts exactly how many microlensing events they should expect to see per year, what the duration of those events should be based on the velocity kicks, and where in the sky these events are statistically most likely to cluster.
By using this computational map, astronomers are perfectly positioned to test their theories against the cold, hard reality of the universe.
The ultimate test.
Right. If Roman and Gaia run their surveys, and they find the exact frequency and mass distribution of microlensing events that the Flatiron simulation predicted, then we have closed the loop. We know our fundamental understanding of stellar death, supernova kinematics, and galactic evolution is accurate. We will have successfully mapped the hidden underworld of the Milky Way.
And, scientifically speaking, what if they don't find what the simulation predicts?
Oh, that's a good point.
What if the yield is far lower, or the mass distribution is completely different? That outcome is almost more exciting.
Because it means we're wrong.
Yes. It would mean there's a fundamental flaw in our understanding of core collapse physics, or the initial mass function, or even gravity itself. It would mean we get to discover entirely new physics to fix the models. Either way, whether the models are validated or shattered, we're on the precipice of opening a completely new empirical window into the dark sector of the galaxy.
It is deeply satisfying to see how modern science operates at this level. You have theoretical physics dictating the rules, you have supercomputers simulating the macro-scale results over billions of years, and then you build highly specialized space telescopes to verify the microscopic distortions in reality that the model predicted.
It is the scientific method scaled up to galactic proportions.
Let's take a step back and just look at the intellectual journey we've been on today.
It's been quite a ride.
It has. We started with a historical view of the universe that was inherently biased, severely limited by our biological and technological need for things to emit electromagnetic radiation in order to be studied. We accepted a textbook paradigm of black holes as these bright, ravenous, highly interactive binary systems.
We built our models on the chaotic, glowing 9%.
Right. And then, by tracing the thermodynamic lives of billions of virtual stars, by factoring in the incredibly violent asymmetrical kinetic kick of a supernova core collapse, we arrive at this stunning paradigm-shifting realization. We're surrounded by a massive, invisible ocean of solitary black holes.
Just drifting.
91% of the population, tens of millions of them, are just drifting silently through the galactic void, and another 3% were kicked with such ferocious energy that they've abandoned the galaxy entirely, wandering the freezing intergalactic space forever.
It's a poetry, honestly.
We've gone from believing we understood the bright inhabitants of the galaxy to realizing we are standing in the middle of a dark, crowded forest filled with unseen leviathans.
This forces an incredibly important philosophical reckoning for the scientific community, I think.
How so?
Well, if our entire understanding of stellar mass black holes, their behavior, their demographics, their formation channels, their very nature was so thoroughly warped by a highly visible, incredibly loud minority.
Yep.
What else are we missing?
Oh, wow. That is a big question.
Right. What other fundamental cosmic, physical, or even biological truths are we currently misjudging simply because the actual majority of a population doesn't draw any attention to itself? In astrophysics, we are constantly in danger of assuming that the phenomena which are easiest for our instruments to measure are the most important forces in the universe.
That's all we can see.
Exactly. This hidden population of 91% isolated black holes is a humbling, critical reminder that the universe is vast, it is mostly silent, and it is largely indifferent to our observational limitations. The most pervasive and powerful forces in nature are often the ones making the absolute least amount of noise.
That is such a profound thought to leave on. The invisible majority shapes the gravitational architecture of the universe just as much, if not more, than the bright, explosive anomalies that catch our eye. So the next time you find yourself out on a clear night, far from the city lights, and you tilt your head back to look up at that glorious glowing band of the Milky Way, I want you to appreciate the light of those billions of fusion engines. But more than that, I want you to respect the dark spaces in between them. Keep looking up, but never stop thinking about the massive, silent things that you cannot see, wandering quietly in the dark right above you.